All right, now we're going to do recurrence relations. And my understanding is that everybody has studied this before, but when we go through the proof of it, people seem muddled anyway, so we're going to go through it. All right, so, we did that already, didn't we? We did recurrence relations already?
Yeah.
Okay, good. So now, that was just a review of what we needed to do. Here, let's talk about the size of the input. All right, I said you can have size, the measure of size be anything you want. So in some ways the input might be getting bigger as long as in your measure it's getting smaller. And I put a bunch of, all right, so here, what is it? It's a function from the input to a real number, right? And if the input is that, right, then I could make my size be n, or I could make it that, right? I could make it anything I want it to be, right? Everybody good? So, so the two things that must be true about your measure. The one is every time you give an input to a friend, it needs to be smaller by that measure, right? Smaller by at least one. And when the input is small enough, sufficiently small, you have to have reached the base case already, right? So I put all these on an assignment once, and everybody struggled with them. So now they're in the slides. All right. So here we're gonna just look at some simple recursive programs, and we're going to analyze how deep they run, right? So here's a program, right? My input is n and m, and if n sufficiently small, then I say hi, and I recurse on n minus 1 and 2m, right? So let's have a vote here. How many people think this well, you first note that the input's getting bigger here and smaller here, right? So how many people think this program halts? How many people think it doesn't halt? How many people have no idea? Exactly. All right. So what do we need? We need a measure of progress, right? We need a measure of size. And since our input's an n and an m, it can be any function of n and m, right? So clearly we don't want it to be m, right? Because m gets bigger. So let's have our measure of progress be n, right? And so is our input getting smaller? And if our input's sufficiently small, do we halt? Yes, right? So let's, does it always halt? M gets bigger, right? The algorithm, the designer gets to decide the size, right? So here, let's trace out on an example and see what happens. Right, on that, right, I have one input that, I guess we're only recursing once, right? So I only have one friend, and that's my friend, right? 3 got smaller, but the 5 doubles, right? And then the 2 gets smaller, and the 10 doubles, and then right? And then we halt. Right? Does that make sense? Just because the m is getting bigger is in some ways none of our business. Right? Our sense of Which one? Where? Oh, this should be 40. I was never good at math. Good. Yeah. You know I won't remember to fix that, but yeah, so that should be 40. And the size is getting smaller. And in fact, on an input nm, what's my depth of recursion? It's n, right? Because it starts out at n, and it goes down by 1 each time, right? So that's good enough. All right, so here's another one. Let's think about whether this is going to halt, right? Here we're stopping when n is small. Here n is getting smaller. Here's m's getting smaller, right? So we have to think, what's our measure of progress? Right? Is it M? Is it M? Does this one halt? Anybody think it halts? This one does not halt, right? And the reason is, well, first we can try to argue that it should halt is, well, what's our measure? Well, our measure can't be N because it doesn't get smaller here. It can't be M because it doesn't get smaller here. So when I see this, I want my measure to be the sum, right? But I stop when N gets small, right? So let's, yeah?
But isn't there a subset of kind of inputs for which it does halt?
Well, let's run it and see. Where are we? We're here somewhere.
Wait, why doesn't n get smaller? I see the n minus 1.
So there you can see the answer right there, right? So here, right, we have two friends, right? One's getting, and here we have two friends, and here we have two friends, and the thing is, you might think, well, some of these paths end, right? If in this path where right, we have here's go left and here's go right, right? And if you keep going left, it's going to halt. So anything down here is going to halt. But what about this path where you just go right, 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 right? Right? Here, n becomes negative and you're going to keep going.
Gotcha.
Right? Does that make sense?
If you just add it in the if statement.
Let's just hold, yeah, you're right. If you mean if you did that?
Yeah.
Exactly. Right? So here, if we halted with either of them, we'd be good. Yeah?
So it could halt, but you don't know what path it's going to take, right?
No, it's taking both paths.
Taking both paths, then why doesn't it halt eventually with the n minus 1?
It does. It does, but it doesn't. If there's an infinite path, you have your tree of stack frames,
Yeah.
and if there's an infinite path, then it's never going to halt. You just have to have one path that's infinite, and it doesn't halt. Right? Right? This path here, I'm going to prove to you it doesn't halt. This path doesn't halt.
That one does.
So what?
So it could possibly.
No, because it does a depth first search on this tree, and the tree is infinitely big.
Okay.
Right?
So just to clarify, the way this is going to work is that it's going to print high for every leaf node in the tree.
Yeah. Every leaf is going to get printed. Yeah, exactly. Yeah.
Sorry, so you would have two stacks, basically, and that's when one of them would halt.
There's a good question, too. Do we have two stacks? No. Remember we covered stack frames, stack of stack frames, and we covered the tree of stack frames. All right? So the tree of stack frames is easier to visualize. It looks like if it has two friends, then it's a binary tree, right? And as we see from here, we don't know that all paths down the tree are the same depth, and here we see that all paths down the tree might not be finite, right? But so the running time is going to be proportional to the number of stack frames. Now, what does the stack of stack frames do? It does a depth first search. So it goes down and then it comes up of this tree. Yeah?
Why does it get to 4 and -1?
Well, because this guy calls this guy, which calls this guy, which calls this guy.
But 4 to 0 shouldn't call that guy
Why not?
because m would be less than or equal to 0.
Oh no, we haven't gotten there yet.
Okay.
Sorry, we're still here. We're still here. We were just warming up. I don't know, that came up and this didn't disappear.
Everybody's telling me it's infinite, and I'm like, no. That
Yeah.
My question is that if we do have the risk of having an infinite loop, why do we use DFS and not
just slow down. I'm not sure which searches you wanted, but if you have an infinite tree, it's going to take infinite time to look at it. I don't care how you look at it. That's the one problem. And the other problem is here we're viewing it as a tree, but in the code, it could be I really need the answer from this before I call here. Right? So I guess it depends on your compiler. A compiler could look at this and say, hey, these two calls are independent of each other, so I can call them in parallel or in any order. But sometimes this call depends on that call. Right? If I take the output here and I put it in again. Did that answer your question? Yeah. Anyway, it's an infinite tree. Yeah.
I got it now, but I think what happens is when you get to that second part with the n-1, it's going to keep calling friends, right? And it's going to keep going forever. So it doesn't matter that the first one gets an answer.
Yeah. I mean, let's give you this guy for free.
Yeah.
Right? Let's suppose I make the code easier where we even delete this line. Right? That shouldn't make it faster. I mean, it should make it slower, right? And it still runs infinitely. Yeah?
Those kids will run to the right and then have the same mission.
Yeah. Yeah.
Not too sure why it's not going to the left, but it's going to the right.
It's doing both. It's doing this whole tree. Oh, you mean why is it doing here?
Yeah.
Well, because I was lazy and I didn't fill out the whole tree. It's a big tree.
Is it because the order of the code?
No. No, the reason the tree isn't, it's a big tree, and the reason it's not all filled out is because I was lazy. I wanted to show you one path in the tree that was infinite.
Oh, okay.
Right? This will recurse, but I didn't put it in the slide. All right, so now let's bring this in, and how does that change things? Right? Now, this is just crying for a measure of n plus n. Right? And the advantage of that is now it's n plus n gets smaller in both cases, right? But now we have to check up here. If n plus n is sufficiently small, say n plus n is 0, then the sum, if the sum is 0, then one of them has to be negative, right? Or 0. Does that make sense? Right? We want to guarantee that if this gets sufficiently small, right? Right? So I didn't change the tree, right? This gets gets removed. Everybody following that bit? Here's a little theorem. If n plus n is less than or equal to 0, then m is less than or equal to 0, or n is less than or equal to 0. Everybody buy that?
Yeah.
And that's what we see how we're using that here? Right? We have our measure. If our measure keeps going down, and when our measure gets sufficiently small, we're guaranteed to meet this exit condition. Right? Yeah?
So it just worked because, like you said, n larger than less than equal to 0, or
Yes.
whatever.
Yeah. In fact, I think our next one, maybe I didn't say it, but here's a good one. What happens if I put an and in here?
Then no.
Then it doesn't halt, right?
Oh, sorry. All that was just for the if statement? For the n plus?
That was just comparing,
Yeah.
this is comparing, this is the measure, and this says if my measure gets sufficiently small, then I exit, right?
Yeah.
And if you change this to an and, right, then we wouldn't exit here, right? We would keep going. Yeah?
If we change the whole into an and, won't it reach a point deep down that it would all be 0?
This path, I just have to prove to you that it doesn't halt. All I have to do is give you one infinite path, right? And this path, the n never changes, right? All right, here's a funny one. And why am I doing this? Just to be funny. And actually, I pondered this while sitting on the subway, and it seems to be similar to the eigenvectors of a matrix, but we don't have to get into that, right? So see how it looks kind of like a matrix, and we have our vector in M, and it transforms the vector, and anyway, right? Now we want to see whether this halts or not, and you can see it's kind of strange. So does it halt? Well, you need a measure, and so that was my measure. And if you wanted to know how did I come up with that measure, well, just I see everything is linear, so I happen to have a good enough sense that my measure should be linear. So I came up with a linear measure A and B. I just put in parameters there. And then I solved for A and B to make sure that it always gets smaller, right? And then that gives me two equations, right? The two equations is this has to get smaller and this has to get smaller. So that gave me two equations, two unknowns, right? The unknowns are the 5 and the 2 are unknown. Anyway, you do that and you see, oh, look at, that gets smaller and that gets smaller, right? Everybody buy that? I don't know. No, you don't buy it? You don't understand it? Here's just some measure. All right. Well, let's first prove to you that the measure works, and then I'll tell you how I got it. All right? Proving it works is we just divine inspiration, get this measure, and then we see what's the measure here? The measure here is 2n plus 2m, right? So what's the measure of this guy? Right? It's 5 times n plus 2 times m. And this is my n and my m. And then I rearrange it, and I see the measure of my friend is 1 less than my measure. Right? And I do the same for this friend. This friend, the measure is 1 less. Right? And then, everybody got the way it works? All right.
And then you just go to the left.
And then how do we make it stop? Again, we have to say if this is true, then this is true. Right? If this thing here is less than or equal to 0, then m is less than 0 or n is less than 0. Right? Now, you might ask, how did I get it to the 5 and the 2? Well, I put variables there, a and b, because I knew it needed to be linear. And I did this math, and that gave me, this needed to be less than that, gave me an equation. And this needed to be less than that, which gave me an equation, and I had two equations and 2 unknowns, and I solved them, and I got 5 and 2. Yeah?
Could you just done n plus m instead of 5 and this 2, right?
No, because actually it wouldn't have gotten smaller. One of them wouldn't have gotten smaller.
Okay.
Right? So, anyway, that was just, well, I don't know why we did that. What's the maximum depth? Right here we can prove, the depth is going to be this. Why? Because that's our measure, and our measure always goes down by 1. Right? In fact, what's cool about the -1 and the -1 is even though it's doing weird things, they're all going to be at the same, it's going to be a balanced tree. They're all going to stop at the same time. Right? Yeah?
Do you kind of just tell by looking at the code, too?
All right. Okay, let's tell by looking at the code.
So, a little harder.
Well, it's not that different, right? It's still minus, plus, just slightly different numbers.
Yeah.
All right? So you can guess that I'm not doing 2 of the same example, so since the last one halted, this one's not going to halt. Right? And so how do we do that? Well, I have a friend, and then have a friend, and I have a friend, and then he has a friend, See that little piece here? Right? What just happened? We're back to square one. Right? Bad news, because that means we're going to run forever. Right? Now, some paths are going to halt, but here, this jaggedy path is going to run forever.
Because like you add and subtract, that's why, right?
Yeah, right? I don't know.
So it is possible for certain paths to halt, but for some of them to run on for infinity.
Yeah.
In that case, that it's a no-go.
Yeah.
You need one path.
Sorry?
You need one infinite path.
One
Yeah.
infinite, yeah.
Yeah. In fact, an important theorem in set theory is that it's called Koenig's lemma. Says that if you have an infinite tree that has an infinite number of nodes, then either there's a node that has infinite degree, or you have an infinite path. And that's Koenig's lemma. Anyway, more than you needed to know. All right.